target 13A, periodic functions, angles, and the unit circle. So this is going to be the beginning of our trigonometry unit. There is a lot of vocab at the beginning just because we have to establish some terminology so that we can use it throughout the rest of the unit. The first is, what is a periodic function? So a periodic function is a function that repeats a pattern of y values or outputs as regular intervals. The way I like to think about a periodic function is it's a stamp that's going to repeat. So if I had a piece of paper and I were to put down a stamp horizontally, I could then pick it up and move it and repeat the pattern all the way down, and the stamp would be connecting itself. One complete pattern is called a cycle, and a cycle may begin at any point on the graph of a periodic function. The period of a function is the horizontal length or the distance along the x-axis of one cycle. So the first thing I want us to look at is two examples here where we're going to identify the cycle in two ways and determine the period. So the first thing I'm going to switch over to is a highlighter so we can kind of highlight each of these. And I can pick any point on the graph. I'm going to start right here at 2, 2. And if I'm going to make one cycle and I'm going to highlight along, I'm going to highlight until I have the complete pattern drawn. So if I keep going down, I get that line segment, but that's not the whole complete pattern, so I have to keep going all the way up to this next peak. And this highlighted part here is one complete cycle, because if I were to think about this as a stamp and pick it up, I would pick up the yellow piece, I would move it here, and I would have another identical piece. Likewise, to the left, I've got a bunch of identical of these V shapes that I'm creating. Now, that's not the only place that I can identify a cycle, or the only way I can. It doesn't have to go from the highest point back to the highest point again. What if I have a cycle that instead starts down here? So let's go down here to -9. If I click this and I keep highlighting, well, that's one portion of this cycle, but I have to keep going all the way down to there. And so this section of it is going from -9 all the way to -5, and this pink one is also giving me a cycle of this graph. So since periodic functions continue to repeat infinitely, it does not matter where a cycle begins or ends. I can choose any point. I just have to make sure I get the whole complete pattern. So if I were to think about this with my stamp analogy, the pink portion here, if I were to take it and stamp it down again, I would get the next mountain, then I'd get the next mountain, and the next mountain. Likewise, I can do the same thing with the yellow one. It's just going to be a different version of this stamp. But regardless of which one I'm using, if I were to put down an infinite amount of them, I would have the entire periodic function. So each one of those is representing our cycle. So we have the pink way, and then we have the yellow way over here. The next thing they wanted us to find is, what is the period? So the period of this is the horizontal length along the x-axis. So it is, what is the change in the x values? Well, if I look at the yellow cycle that I have right here, it started at 2. So if I'm writing this down, I have the yellow cycle that is starting at 2. And it's going from 2 all the way to 6. Well, if I want to figure out what the distance of that's going to be, it's going to be, what is the difference there? So the period for this is going to be my final portion on my cycle, my final x value, minus my initial x value. So our period length there is 4 for the yellow one. Now, since these are both representing the same cycle, then they should have the same period length. So if I go over here to this pink one, we're starting at -9. So if I'm looking at the pink version instead, we're going from -9 all the way to -5. So if we were to calculate the period on that, it'd be my final, which would be -5 minus my initial, which is 9. So I end up with -5 plus 9, which also gives me 4. So regardless of which way we computed the cycle, the period length is still the same. Okay, let's look at this next example. I want you guys to pause the video and try drawing the cycle in two ways and see if you get the same length of the period for each. Okay, let's take a look at this graph. So I'm going to use the x value 2 again, and I'm going to pick 2, 4 and start here. Now for me to get the whole length of the cycle, I have to keep drawing all the way down to here, but I have to keep going because I have to have the rising portion of this periodic function as well. And then I would stop right at the next peak of that valley. So I have this whole kind of V-shaped graph that I'm getting. Alternatively, I could have one that maybe starts at 0, and if I draw this, it's got to keep going up, and it's got to take that mountain. Now, I can't stop here because if I were to use this as my stamp, I would never get the low portions of the graph, so I have to keep going all the way until I reach the x-axis again. So in this case, these two look kind of much more different than they did in our first example, but both are a complete cycle. So here in the pink, I have to keep going all the way, and I can't just do one of the mountains, I also have to do one of the valleys so that I get both the top portion of the graph and the bottom portion of the graph. Likewise, if I already start at the top, I have to dip all the way down to the bottom and then go all the way back down to the top. So one thing you guys might be noticing is that anytime I pick a cycle, it has to start and it has to end at the same y value so that my stamps can end up connecting. And that's a very important thing about periodic functions, is that they start and they end. A cycle of them start and end at the same y value. Now if we're going to calculate the length of the period on here, let's look at the yellow one first. So the yellow one is going from 2 all the way to 10, and the pink one is going from -8 all the way to 0. Well, if I calculate the distance between those two, it's going to be final minus initial, which in the first case gives me 8. So hopefully in the second case I get 8 as well, and we get the final of 0 minus the -8, which is also positive 8. So regardless of which way we looked at the cycle, we get the same period length of 8 for this periodic function in example B. Okay, let's kind of look at another example. So question 2 says, does the following graph represent a periodic function? Explain. Well, I want you guys to pause the video right now. You guys decide if you think it is a periodic function or if it is not a periodic function. Well, let's go back and try to see if I can get a cycle. So if I just start at 0, I'm at 0, 1, it dips down, and then I know I need to end at the same y value, so I have to go back, but no portion of this, even if I go all the way to 1 again, they start and they end at 1, but if I pick this up and repeat the pattern, it would just stay at the same distance across. It never can climb again. So even though this looks kind of like it should be a periodic function because I'm seeing a pattern repeat, it is not going to be a periodic function because of the issue that each cycle is kind of one above the previous one, so there's no way to connect them all the way. So in this case, I do not have a periodic function, so this is not one, and the reason being is that the y values each section of them, so each y value section, does not repeat to another one. So if I were to try to line them up, I would just get the next one. There's no way to keep growing higher. When I look at both of these, they have the same horizontal highest point and they have the same lowest point, regardless of where I am on the cycle, versus this keeps growing over time, which is not what a periodic function does. It stays kind of bounded on top and on bottom by something that is called the amplitude, which we will talk about later. Okay, let's move on to kind of a little bit of review. So in geometry, you guys learned about the special right triangles, the 45, 45, 90, which is shown below, and the 30, 60, 90, which is also shown below down here. And these were the side lengths that you learned in geometry, and I'm going to guess your geometry teacher told you you guys got to know these and maybe memorize these triangles. Well, we're going to use this stuff from geometry, but instead now we're going to take all that information and put it onto a coordinate plane. And because we're in an algebra class and we're focused on, well, how does this affect the x and the y axis, we're going to end up taking these triangles and putting them on a coordinate plane. When that happens, we only care about when our hypotenuse is going to be equal to 1. So because this is a trig class, I don't want to use the same x root 2 and x for the legs here, and then the hypotenuse being 2x. I want to make sure my hypotenuse is always equal to 1. And the reason being is that we will end up being on something called the unit circle from here. So if I'm going to make this equal to 1, then these values end up changing. So let's look at the 45, 45, 90 triangle. And I want to make my hypotenuse, which is x root 2, I'm going to set this equal to 1 because I really want my hypotenuse value to be 1 instead. Now when I do this, I need to solve for the x value here so that I know what my side lengths are. So if I have 1 equals x root 2, and I want to solve for x, well, I would divide through by root 2, and I'd end up getting x equals 1 over root 2. But we know from last semester we're not going to leave square roots in our denominator, so I need to rationalize this fraction by multiplying by the square root of 2. Ooh, technical difficulties there, let me fix that. So we need to multiply by the square root of 2 over itself, which ends up getting me an x value that is going to be equal to root 2 on top, because I get 1 times root 2, all over, well, when I go root 2 times root 2, I end up getting the square root of 4, which is just 2. So by making the hypotenuse equal to 1 here, this is a choice that we had to make, which we're going to make because we're on the unit circle. What that then tells me is that instead of calling the legs x, I'm going to call this leg root 2 over 2, and because they're equal, since this is a 45, 45, 90 triangle, they both are going to have legs equal to root 2 over 2, and the hypotenuse here will be equal to 1. Now we can do the same thing over here on the 30, 60, 90. So in geometry, we called the hypotenuse 2x, we called the angle opposite 30 degrees x, and we call the side opposite 30 degrees x, and we called the side opposite 60 degrees x root 3. Well, I'm going to do that same thing and set my hypotenuse equal to 1, since that's where I'm going to need it to be on the unit circle. When I do that, I have 1 equals 2x, so if I divide through by 2 on both sides, I end up getting x to be equal to 1/2. What that tells me is that the side now opposite the 30 degrees, so across from the 30 degrees, is going to be equal to 1/2, and the side across from the 60 degrees, if I replace x with 1/2, is now going to be root 3 over 2, because I get 1/2 times root 3, which is really root 3 over 1. So when I multiply directly across, we get root 3 over 2. And our hypotenuse is going to be equal to that 1 value. These are going to be the triangles that we are much more interested in for trigonometry, and that are going to be more helpful because the hypotenuse is going to be 1, and we're going to need that as we move forward. So down below here, that's kind of our big idea, and I've rewritten them so that you have them as a cleaner version. You've got to make sure that we have both of these triangles memorized come our next class. So on the 45, 45, 90, both legs are going to be root 2 over 2 since the angles are equal. Our hypotenuse will be 1. On the 30, 60, 90 triangle, the side that is opposite 30 degrees is the short side of the triangle, which is the 1/2 value. So I think about this as the short side, since it is opposite the tinier of the two angles. So here's our short side down here. The reason it's the shorter of the two sides is that 30 is the smaller angle here, so that the side opposite that will be the shortest. And then our root 3 over 2 is always across from the 60 degree, and I consider this our long leg, or our long side of it. Now, of course, the hypotenuse is always going to be our 1 value there, since we are on the unit circle. So really do take the time over the next couple days to make sure that you have these memorized come our next class, because this is going to be how we find our trig values for any angle on the unit circle. Now the next thing we're going to talk about is some terminology for how is this going to work on a coordinate plane. So we've looked at angles inside of shapes in geometry class, but we need to look at, well, how does this work if I'm on now an x and a y axis? So the first piece of terminology we have is, what is an angle? So an angle in a coordinate plane is in standard position when the vertex is at the origin. So the vertex of my angle is right here at the origin, and one ray is on the positive x-axis. So this is this green side right here on my positive x-axis, if I were to write it. Now this ray on the positive x-axis that I have in green is called the initial side, because anytime we're going to find an angle on a coordinate plane, we are always going to start at the positive x-axis here and then rotate from there. The other ray is called the terminal side. It's where the angle ends. So in this case, I drew the terminal side in quadrant 3. Now it could end anywhere. I just did it in quadrant 3 as an example. And so my angle starts at the positive x-axis, which is my initial side, and I decided to rotate up and over down to into quadrant 3 for my terminal side. So this angle here, which is going to be bigger than 180 degrees since it's more than a straight line, this is going to be my angle that I'm calling theta. So we are going to look at some Greek letters in this section, and just to make sure, that is the Greek letter theta. We're also going to see a couple more as we keep going. But this will be how we'll draw any angle on a coordinate plane. We always start at the positive x-axis, and in this case I'm rotating counterclockwise. I could rotate clockwise, and we're going to look at what is the difference between those two next. But the key right here is you always need to start each angle on the positive x-axis. Okay, so let's look at what happens when I rotate two different ways. So in this first example, it says the measure of an angle is positive when the rotation is, in this case, counterclockwise. So I'm going to fill in our blank here. So when I take an angle, and remember I'm starting on the positive x-axis always, and when I rotate up and over to the counterclockwise direction, this, in this case, theta, is going to be a positive angle, because I'm rotating counterclockwise. And that's just the definition that we have in trigonometry. Now the measure of an angle is negative if the rotation is going to be clockwise. So I can rotate clockwise, that's okay. Again, I have to start at the positive x-axis, so my angle is starting here and is rotating down and over. And in this case, our angle, which I'm still calling theta, is going to be a negative value since I'm rotating clockwise in this case. You might notice that both of these angles are ending at the same terminal side, and there's a special relationship that happens when we have two angles that do that. Because I can rotate counterclockwise, which would give me a positive value, versus clockwise, which would give me a negative value, I have this special relationship between those two angles. So two angles in standard position are called coterminal if they share the same terminal side. So in this case, I have one angle on the top, which is, remember, both of them are starting at the positive x-axis. So as they're both starting at the positive x-axis here, this angle on the top, which we're calling angle alpha, is rotating counterclockwise up and around. This would be a positive value since it's rotating counterclockwise. And then angle beta starts at the positive x-axis and rotates down. This will be a negative value because of the direction that we're rotating. But both of these angles, we would say that angle alpha and angle beta are coterminal since they end at the same terminal side. Now, they also start at the same initial side, but every angle starts at the positive x-axis. They just both happen to meet up on the same terminal side, so they are called coterminal. Okay. Now, before we get into some examples with coterminal angles, we need to be able to know where stuff is on this unit circle. So here's our next big idea. So I have the unit circle drawn below with a bunch of kind of terminal sides drawn at it so that we can label this. So what makes it a unit circle is that it has a radius of 1. So if I look at this circle, no matter, I have my origin, I have my center at the origin at 0, 0. Each one of these rays is representing the radius of here. So each one of these values is having a distance here of 1 because I'm on the unit circle. The other thing we need to keep in mind is that a circle has 360 degrees. So I'm going to start on my positive x-axis. So I'm starting right here. This is actually going to be the angle 0 degrees. Now, because a circle has 360 degrees, if I rotate counterclockwise and go up and all the way around and end up back at 0, that is also equivalent to 360 degrees because that was one full rotation around. Which means if I only go halfway around, this guy over here is going to be at 180 degrees because that would be half of 360. And I'm going to continue kind of halving things. So if I half between 0 and 180, I'm at 90, which is this top angle up here. And if I half it between 180 and 370, I'm down here. Between 180 and 360, I'm at 270 degrees down here on the negative y-axis. Those are all of our angles that are on an x or a y-axis. So I've got 0 degrees, 90, 180, 270, and then all the way back where 0 degrees is. Although I'm saying equal, what I really mean by this is they are coterminal, because they are starting and ending at the same terminal side. Now let's find all the angles in between. Well, this value in the middle is halfway, so halfway between 0 and 90 would be our 45 degrees. We're seeing an angle that looks familiar from some of our triangles from before. And if I do the same thing on all the halfway points between 90 and 180, halfway between that is 135 degrees. And if I go halfway between 180 and 270, that would be 235 degrees. And if I go halfway between 270 and 360, that would be 315 degrees that we have. Now the next angles that I have to find are what are these kind of in between those. Now this I have to give you as a definition, but the first angle that we're interested in looking at is going to be our 30 degrees, which will go back to that 30, 60, 90 triangle. And there's a pattern that happens here. So the first angle that you get in this first quadrant, I added 30 degrees to it. To get from 30 to 45, I'd add 15 more, which means to get from 45 to the next one, I'm also going to add 15 degrees to it, which gives me the next angle of being at 60. And then to get from 60 to 90, we added 30 more degrees. This pattern is going to repeat in every single quadrant, which means to get to my next value, I'm going to start here again, and I'm adding 30 degrees. So from 90, if I add 30, we're at 120. Now it makes sense that if I add 15, I get back at 135. If I add 15 again, we're at 150, which if I add 30 gets me to 180, so I'm doing everything right so far. If I add 30 to this, I get to 210 degrees. If I added 15, I'm back at 235, which we already found. Now when I add another 50, I'm sorry, that should say 225. Ooh, that's a big problem. That should say 225, not 235. Halfway between 180 and 270 is 225. A little bad arithmetic there. I'm sorry, you guys. Make sure you do edit this in your notes so it says 225. When I add 15 again, I'm at 245 degrees, and then when I add 30, I'm back at 270. Now from here, the last quadrant is going to repeat the same pattern. When I add 30 degrees to it, I'm at 300, which makes sense to get me to 315. If I add another 15, I'm at 330, which to get me all back to where I started when I add 30 degrees to this, I end up at the 360, which is coterminal to 0 degrees. Now this unit circle, just like our special right triangles, is going to be extremely important that you guys know where each one of these angles is on the unit circle. And this is really going to come through practice of practicing drawing all of these angles here so that you guys get used to it. But there is this pattern that works around it, and I wanted to point it out to you guys. So the biggest thing that we start with is that a circle has 360 degrees. So if I start at my initial side and I don't move at all, then my angle is 0 since I didn't move. But if I take this and I rotate all the way around the circle, then I'm back at 360 degrees. So 0 and 360 are coterminal to each other. From there, I'm kind of using this halving concept. So to get the spot on the other side, it's going to be half of 360, which is 180. So 180 is over here on the negative x-axis. I then half that to get what's happening on the y-axis. So half of 180 is 90. So I'm on the positive y-axis. And then half of 180 and 360, if I add them together and I half them, I get 270 degrees down here. From there, I have this pattern repeating in each quadrant, where my first angle is 30 degrees, then my second one is 45, and then 60. And what's happening in between each one is I'm adding 30, then I'm adding 15, 15, and 30 again. And hopefully this is making sense in your mind and adding up that if I take 30 plus 15 plus 15 plus 30, I would get to 90 degrees, which is another way to think about how I got from 0 to 90 up here. We would take this pattern and continue to repeat. So when I add 30 degrees to 90, we're at 120. I then only add 15 to get me to the halfway point, which is 135. Add 15 to get to 150, and then another 30 to get back to 180. And then it continues on from there. So we add 30 to get to 210. We add 15, which gets us to 225. I hope you've corrected that in your notes. And then we add 15 again, which gets us to 240. And then we've added 30, which gets us to 270. I add another 30, and I'm at 300. Add 15, and then add 30. The follow-up questions I want to ask you guys with these is, what do you think happens if we keep going around the circle? And what happens if we go clockwise around the circle starting at 0? So each one of these we went counterclockwise. What do you think will happen if we go clockwise around? Why don't you guys pause the video right now and answer both of those questions for yourself? What happens if we keep going around the circle? And what happens if we go clockwise around the circle instead, starting at 0? Well, let's address the first question. If I keep going around the circle, I'm going to just have values that are bigger than 360 degrees. So if I keep going around this circle, I'm just going to get something that is bigger than 360 that is coterminal to one of these angles. So let me switch colors real quick, and let's look at what happens if I start at the positive x-axis. I'm going to draw it for us. I go all the way around the circle, and I end back up at the angle here that is coterminal to 30. So when I'm using this equal sign, I do mean coterminal. So when I look at this, really what I did was I went all the way around, which is 360, and then I went another 30 more. So this angle would be 360 plus 30, which would be equal to 390 degrees. So for each one of these values that is on our unit circle, between 0 and 360, from just one rotation, they have actually an infinite amount of angles that are coterminal to themselves if I keep rotating around. So if I rotate once around, I'm adding 360 to it. If I rotate twice around, I'm adding 2 times 360 to it, and I can keep doing this as many times I want. So what happens if I keep going around? We're adding multiples of 360, depending on each time you go around. So if I go twice around, remember, I'm adding multiples of 2 times 360. Now, what happens if we go clockwise, starting at 0? Well, I hope we're remembering that if I go clockwise, I'm going to get a negative angle. Both of these are producing angles that are going to be coterminal. So we are finding coterminal angles to the original stuff already on the unit circle. So let's do one where if I go counterclockwise and I start at 0 and I rotate to here, well, if I go to this guy, this would be equivalent or coterminal to negative 90 degrees because I moved 90 degrees total down because it was a quarter of the circle, but it's negative because I'm rotating clockwise here for this angle. And I could do this for any point on here. If I take this guy and I rotate counterclockwise, and let's say I go all the way to where 210 is, then I would say that this angle, well, I went negative 90, then I went a little bit more. This is actually negative 150, and those guys are coterminal to 210. And I can do this for any spot on the unit circle. Let's jump into some examples. So the first thing we have is it says, draw a sketch of the given angle and find 2 additional angles that are coterminal to it. So I want you guys to pause the video right now and sketch out where each of these angles are, and try to do it without looking at the prior page of your notes. Okay, let's look at the first one. So 120 degrees. What I'm going to look at is I'm starting at 0. I know that 180 is over here. I know that 90 is up top, and 270 is down here. This kind of helps me decipher which quadrant will I be in. Well, 120 is a little bit past 90, so that would be this angle right there, which is this 120 degree rotation right there from the positive x-axis, a little bit past the y-axis. Now, if I want to find 2 angles that are coterminal to it, one way to do that would be, well, what if I go past 120 and then go back to it. So one angle would be if I take my 120 that I have and I do a whole nother rotation on it. So I go to 120, but then I go a whole nother rotation around, so I'm adding 360 degrees, which would give me an angle of 480 degrees. For this guy would be one option that is coterminal, and that would be, I'm going to do that one for us back in pink. So the 480 degrees would be drawn if I start here, I go all the way around past it, and then I go back to the 120. Now it wants me to find two angles that are coterminal, so I've got to do one more. Well, the next one that I could do is I could go twice around, but let's practice some negative angles. So the next one would be if I start here at the positive x-axis and I rotate clockwise down and I go around. Well, that would be the same thing as if I go 120 minus 360. Because remember, 360 is the entire circle, and I stopped short of 120 degrees, so it's my 120 minus 360, which will give me negative 240 degrees there for that green angle. Why don't you guys try to find two coterminal angles for both example B and example C? Okay, let's look at 210. So I'm going to go back to labeling my axes. So I have 0, 90, 180, and 270 degrees. So 210 is going to be somewhere here in quadrant 3, and it's the first angle past that 180 degree mark. So that right there is going to be my 210 degree angle. Let me actually label it out here so that I don't end up drawing over it in a little bit. The next thing I want to do from here is I want to find something that's coterminal to it. So the nicest route that we could take is, well, if I start at the positive x-axis, let's go past it and then go all the way back to it. So that would be this case where I took my 210 and I added a rotation of 360 degrees to it, which would give me a value of 570 degrees if I add one rotation to it. Now, I could add another rotation to it, but if I want to get a negative angle and get that practice in, remember I'd start at the positive x-axis and I'd rotate down here to get this other angle that is coterminal, and that would be equivalent to taking 210 degrees and subtracting 360, which will give me a negative 150 degrees. So remember, I'm finding angles that are coterminal here, which means in this example is that 210, 570, and negative 150 are all coterminal. Now technically for each one of these angles, I get an infinite amount of angles that are coterminal because I can keep adding more revolutions around this and just keep adding 360 degrees. Let's do our last example here. So 315, if I go back to labeling these, I've got 0, 90, 180, and 270. Well, 315 degrees is bigger than 270, and it's actually the halfway point here between 270 and back to my 360, if I'm thinking about those as being coterminal. So this right here, starting at the positive x-axis and rotating around, is 315 degrees. Now to find something that's coterminal to it, I'm going to take the first one and just rotate past it. So start at the same spot, go up and around, past it, and then all the way back to it. Quite a big rotation there, but that would be taking my original angle of 315 and adding 360 degrees to it, which would end up giving me 675 degrees for that really gigantic angle. Now I can do the same thing, but now I'm just going to take the negative angle. So if I start here and I rotate down, so I'm rotating clockwise, I'm getting this little itty bitty tiny angle, which will end up being negative because it was my 315 minus my 360, which is actually negative 45 degrees on that guy that we end up getting. Remember, I could find more coterminal angles. I just keep rotating either positive, so counterclockwise, or rotate negative, which would be clockwise on this. Okay. The next portion of this we're going to start introducing is sine, cosine, and tangent, but we're going to wait and do that in our next lecture. what I need to make sure you guys have down between now and then is not only the terminology, but we really have to make sure that we know where all of the angles are on the unit circle. So I have all of these memorized at what spots they're at, and I think the easiest way is to just keep writing it down and practicing them and doing some more examples where you're drawing angles and finding two more that are coterminal. So this is one thing that we have to have memorized, which is the unit circle values. The next thing you really want to have down is go back to your 30, 60, 90 triangle and your 45, 45, 90 and make sure we have the sides of these triangles memorized. Remember, the hypotenuse is always going to be 1. And then if a 45, 45, the legs are equal, so they're both root 2 over 2. And then in the 30, 60, 90, if the hypotenuse is 1, the side opposite 30 degrees is my short side, which is 1/2, and the side opposite 60 degrees is my long side, which is the root 3 over 2. So those are the two big things we've got to have kind of down in our head before we move into finding values for sine, cosine, and tangent in our next lecture.